Hello everyone, my name is Steve Tran and my partner is Joshua Genova. Our project is on reinforcement learning for autonomous guided vehicles. We'll start with a brief introduction. So the motivation behind our project is that logistics and manufacturing have introduced these automated guided vehicles to help with their workflow. As a society, as we increase our demand, supply and demand, we're going to need help with these automated vehicles to just get these products to the end user as quick as possible. Here are some AGVs that you may be familiar with. The orange robot in the middle is Amazon's implementation. These robots lift up the shelving units to kind of move around where the items are in the warehouse, so it's a little bit easier to grab. And the two images on the right are car manufacturing assembly lines. The Kuka robot on the top is transporting this chassis in replacement of a conveyor belt. And the bottom image is showing these Tesla AGVs that are following this line strip on the factory floor that will guide it to its next destination. What's nice about that is if you want to reorganize your assembly line, all you would have to do is repaint that strip so then it would follow a new path. And the robot in the bottom middle is the ABB double arm Yumi that is transporting these test tubes around the research lab. And lastly, the image on the left was taken just a few weeks ago. I was walking around campus and I saw these Starship delivery robots, and they got stuck behind this UPS truck because it was past their boundary of their range on their proximity sensors. So this is where RL comes in to help these AGVs navigate and learn how to maneuver around these objects.
For our literature review, we have 5 papers. The first one is what they did is they used lane finding, waypoint navigation, object detection methods in Carla, which is a simulation environment using ROS to test their reinforcement learning algorithms. The second one is they used deep-Q learning using with Turtlebot 3 in ROS, and they simulated in Gazebo. We were going to try this paper, but due to compatibility issues, we weren't able to do this. The third one is to navigate. What they did is they navigated in unknown rough terrains. This is pretty important since normally what we see is it's just a normal, like a street uniform terrain, and with rough terrains it makes it much harder. And they use deep reinforcement learning with reward shaping. The fourth one is similar to what we're going to do in this paper, which is collision avoidance with pedestrians using the algorithm GA3C, CAD-RL, which stands for GPU CPU asynchronous advantage actor-critic for collision avoidance with deep reinforcement learning. I believe this is closer to the state of the art. This is a newer paper than what we're doing in this project. And the last one is it combines deep reinforcement learning and robust linear quadratic regulator for vision-based control of AGVs. Again, this is probably one of the state of the arts because it combines two methods, and it's also vision-based as opposed to just knowing the positions. For problem formulation, I'll be talking about what we'll be doing in our project. First, we want to define reinforcement learning, and according to Sutton Bardo, which is one of the books we talked about in class, is reinforcement learning is learning what to do, how to map situations to actions so as to maximize numerical reward signal. And this is a figure that they used in their book. So to use reinforcement learning, we first define the Markov decision process. And in what we'll be doing in our work, we have an agent, state, action, reward, and environment. So our agent in our project are the robots or the robot vehicle or the humans. The state are the position of robots or humans, and the action is just the velocity of the robot. And in the paper that we're using, this is the reward that they use. And then our environment is simply a Python simulation environment with humans and a robot. The RL algorithms that they use in this paper are ORCA, which stands for Optimal Reciprocal Collision Avoidance. This is what they use for the humans in our environment. The other two are CAD-RL and LSTM-RL, which stands for Collision Avoidance with Deep Reinforcement Learning. and long short-term memory reinforcement learning. And they use these two as a baseline to compare their work. So what we're actually using is called CrowdNav and SARL. So the paper is called CrowdNav, which stands for Crowd-Aware Robot Navigation with Attention-Based Deep Reinforcement Learning. And their algorithm is Socially Aware Reinforcement Learning.
So our approach and goal to this project is we want to get better results in half the episodes that was used in the CrowdNav paper by changing hyperparameters. So the reason why we chose 5,000 episodes as our goal was that in the lower episodes, there wasn't really any good results until after 2,500. Here are some visual aids to show you the differences between 500 episodes versus 5,000 episodes. With 500 episodes, the robot never reaches the goal. With 5,000 episodes, CAD-RL and LSTM-RL don't quite make it to the goal, while SARL is able to reach the goal in just a little bit over 12 seconds. Now we will talk about our results. First, we took the baseline of each RL model and broke it up into components for comparison. Here you can see LSTM-RL has the worst performance out of the three, and you'll see that as a common trend. CAD-RL has a better performance, while SARL has the best one out of the three. As you can see, SARL has a smoother success rate overall, while with collision rate, it's able to get closer to 0 as it approaches 5,000 episodes. And with the robot's time to reach the goal, SARL is the only model that is able to get close to 12 seconds.
So as part of our experiment, we did hyperparameter experiment tuning, and we played around with learning rate, batch size, number of samples in each episode, and epsilon start number. So the baseline, as you can see here, is this one, learning rate of 0.001. And we use 0.1, 0.01, and 0.0001. And we can tell here that comparing to the baseline with 0.1 and 0.01, it definitely improved the reward. And as you can see here, from 0.25 closer to 0.28, 0.27, now we have 0.30 here, around 0.30 here. But with the 0.001, it actually made it worse with 0.14 after 5,000 episodes. Another thing is the batch size. Again, our baseline with batch size is 100. And we played around with 50, 500, and 1,000. So with 50, here, there wasn't much there's not a lot of difference from the baseline. With 500, it made it much worse. And with 1,000, it made it better, but the trade-off here is the more batch size you use, the longer it takes to train the model. So later on, we'll be talking about a mixture of hyperparameters. The next one is number of samples in each episode. Our baseline is 1, and we used 5 and 7 to test. With these two, it improved it in a sense that it's a smoother curve. So which means there's less, it seems like there's less collision rates with this. And it's increasing throughout, as opposed to with the baseline, nothing happens at the very beginning and it jumps up. But the trade-off here is it takes a really long time to train these. I think with 7, it takes a day and a half, and with 5 is something around a day to train these. So definitely there's a trade-off here. Lastly, we have epsilon start. The baseline is 0.5. Then we increase it to 0.6 to 0.9. With, for some reason, with 0.6, it was the results were really terrible. It even goes to negative, and it didn't increase much towards the end to 0.03. And then with 0.7 to 0.9, again, there's not much of a difference. With 0.9, actually, the results were a little bit worse, and 0.7 and 0.8, not much of a significant improvement from the baseline. So we decided to keep the 0.5. So for the discussion part, we'll be talking about 3 experiments where we mixed up the hyperparameters. So with the first one, we changed these are the hyperparameters that we used. And for the cumulative discounted reward, it definitely improved it from the baseline. It also decreased the total time to reach the goal. And as you can see, the success rate, it went up right away. The collision rate is less erratic than the baseline as well. For experiment 2, these are what we used, a little bit of change from our first one. I want to say that experiment 1 took 32 hours, experiment 2 took about 35 hours. So the learning rate changed it a little bit, and with it definitely improved the reward as well as the decrease the time to reach the goal, and it's similar with the success rate and the collision rate here. And with the third one, this one took about I want to say 37 hours, and it still improved the reward. Not much of an improvement from the previous experiment. Likewise to the time to reach the goal and success rate and collision rate. So we would say that the experiment 2 would be our best one, since our reward is more than 0.30, maybe 0.32, 0.33, and it definitely decreased the time to reach the goal.
For our conclusion, we contributed by obtaining a higher reward with less episodes, produced less collision rate while having more success, and lastly, reduced the amount of time needed for the robot to reach the goal. For future work, we want to reduce the duration of training time by changing hyperparameters to see if we can reduce it from the 35 hours that we had mentioned before. We also want to incorporate computer vision or other sensors. And lastly, we want to implement smoother vehicle movements. Here are the references used for this project, and thank you for watching our video.